Hello there, this is section 2.10 on resonance structures and how to draw them simply by knowing the patterns that come with simple resonance structures. So your book has a fairly lengthy section written on this, and that will probably be a good thing to look at as well. I'm going to do my best to um, give you an addition to what your book has. That way you have a couple extra or more than one set of info that you can look at. All right. So if we remember, we'll do a flashback into what we learned before is that we can have resonance structures in general, right? If we have some double bond, like this carbon double bonded to an oxygen, a resonance form can occur like this very simple one. With a partial or with a negative oxygen and a positive carbon. And of course, it can go back as well to give us our original structure. Okay, so this is in general what a resonance form is, but how do you know what the arrows do, where the electrons go, and where the electrons end up? Well, it turns out that for just about every case that we'll see in this class, almost every case, probably, there are five, I think, general types of resonance movement that you can expect to use. And we'll go over those here. So let's look at the first one, number one, and that's called an allylic lone pair. So first, let's deconstruct the word allylic. Allylic is organic chemistry speak for a position that is next to a double bond. So you have a double bonded pair of carbons here, but then the carbon neighboring that double bond is the allylic position. So when we say allylic lone pair, that means there's a lone pair of electrons at that allylic spot there. Okay. So an allylic lone pair, let's use green, has a resonance form like this, where the lone pair, since it's also in a pi orbital or a p orbital, let's draw that out so you can see. I'm going to try and draw this. So let's, there we are. So this is just the three carbons. And here are the p orbitals of those three carbons. And remember, there's one electron there, one there, but two here, right? Because it's a lone pair. Okay, so what can happen is that this lone pair of electrons can switch where the double bond is and cause this lone pair to end up on the other carbon. When that happens, the resonance structure that you form looks like this. Let's redraw that. That looks pretty bad. There we go. It's the opposite structure, right? Because now the lone pair is on this leftmost carbon instead of the one on the right. And of course, it can go back exactly the same way it came. To make our pair resonance structures. Now, I want you to notice how I've drawn these arrows. The arrows went from a double bond and they went to an atom in one case. And the other arrow went from a lone pair to a bond, and that's where the head was. So remember, you need to draw arrows starting from a lone pair or a bond and ending at a bond or an atom. Those are the two places that they can go. And they must start, the head of the arrow, the pointy part, should tell us exactly where the electrons end up. Okay, now what's kind of cool about this allylic resonance form is that while I used an all carbon example, there are several examples that don't have carbon at all, or at least don't have carbon with the lone pair, and that have maybe funny looking double bonds as well. So we could have an example like this. Where the lone pair of nitrogen can now act as the allylic lone pair, pushing up the double bond between the carbon and oxygen to be just on the oxygen to leave you with a structure that looks like this. And that's called an amide functional group here, if you remember. And when this resonance form interchanges to this one on the right, it can also change back. See how the head goes to the bond there? And the tail starts at a bond and ends at an atom. There we are. Okay, so that is the allylic lone pair pattern. The next type of pattern that we can have is the allylic carbocation. So we do that in blue. Allylic carbocation. So it's kind of the same idea, except instead of a lone pair like this, now we have a carbocation. And this works because the carbocation also is in a p orbital. We can draw that kind of like we did before. So remember, we have the p orbitals. And these p orbitals have some electrons, but the other one does not, has nothing, just a positive charge. Even so, you can have a resonance form that looks very simple where you form the other resonance structure, and then it can also go back to close the resonance form. Okay. So that is the very similar to an allyl lone pair is the allyl carbocation. And there are some examples of these, but fewer. Like for instance, if we look at conceptual checkpoint 2.19, it gives some examples here. So this is 2.19. Gives this example. And here you could see that this double bond could go towards the carbocation, ending in the bond between the carbocation and one of the double bonded carbons. And when it does that, the resonance form that you see has this structure. There we are. All right, great. Okay. Another kind of interesting example here. Let's see, that would be D, the example D there. Oh, I'm really bad at drawing these. gotta start from the other side. 1, 2, 3, 4, 5, 6, 3, 4, 5, 6, 7. There we go. Okay. So now this is conjugated throughout this 7-membered ring, and the resonance form can be as easy as this. Where now you have positive charge here, or it can be a little more complicated. Sorry, I gotta get better at drawing these. Maybe a different pen would work. There we are. Okay. You could actually go all the way around the ring to put the carbocation here instead. Okay, so now the next example we have, number 3, is a lone pair next to a carbocation. Okay, and in this type of example, it's fairly straightforward. It's actually very similar to the one that I used in the very beginning example, which is, let's say you have this type of molecule. A simple resonance form of this can be shown here, where you just migrate that positive charge onto the oxygen. And these aren't typically great resonance forms because oxygen doesn't like to have a positive charge, but that is a thing that can exist. More often, oxygen isn't the best example here. More often, a better example is something with nitrogen. Nitrogen doesn't mind having a positive charge. And so this structure is much better. Yeah. And so this is kind of like the conceptual checkpoint. This is basically A. Yeah, if we add one more carbon, this is conceptual checkpoint 2.20 A. Okay, so the fourth type of pattern that we have, number 4, is a pi bond between, now let's call this a polar pi bond, meaning that both atoms in the pi bond have a difference in electronegativity, a polar pi bond. So this means something like carbon to nitrogen, carbon to oxygen, etc. So in these types of resonance forms, like let's say that this had this structure, a simple resonance form would be for the double bond to go up onto the nitrogen, yielding you positively charged carbon, negatively charged nitrogen. And of course, just as always, that can be reversed too. And I like to put everything in brackets. A fairly simple and straightforward type of pattern here, but one that exists nonetheless. And you can basically do this with any polar bond, like in 2.21, B, they use this example, where of course you could have the same thing occur, leaving you, well, this molecule, which can have the reverse happen as well. There we are. Okay, so for our last trend, we have simple conjugated pi bonds in a ring. So this is fairly straightforward and kind of boring because they don't typically contribute a lot in terms of energy, but in a ring, you can just have each of the pi bonds kind of do a shuffle, leaving you with the same exact structure, but all the pi bonds have shifted one way. And just like the others, they can also go back. Oops. There we are. And these are in brackets as well. All right, so these are the 5 patterns that you should be looking for in resonance drawing. And it just turns out that there's a nice little table in your book shown here. Figure 2.6 gives you the summary of the 5 patterns for drawing resonance structures. So this has been section 2.10.